Visualizing high-dimensional data in 2 dimensions can be a powerful way to gain insights into its structure. However, creating these 2D embeddings often involves making trade-offs, which can lead to distortions or misleading patterns. As data scientists and researchers, it's important that we understand the quality of these embeddings so that we can make informed conclusions about the data structure and avoid potential issues in downstream tasks. That's where Trace comes in. Our tool helps you analyze the quality of 2-dimensional embeddings by providing a range of measures and an interactive interface. By using Trace, you can understand where your embeddings are trustworthy and which patterns are reliable. In this video, we'll be walking you through a possible analysis workflow using a biological dataset of approximately 80,000 cells. We pre-computed the embeddings and quality measures, which took less than 10 minutes. In Trace's user interface, you can select any of the pre-computed embeddings and choose to color the points based on metadata, quality measures, or the original high-dimensional features. Let's start by looking at the landmark distance correlation, which tells us if the global arrangement of a point is preserved in this embedding. We observe that this part down here, for example, has a low score. To understand why its position in the embedding might be misleading, we can select a point and visualize the approximate high-dimensional distances to all other points. We discover that these two parts are actually very close to each other. When we move to a different embedding, we notice that they move closer together and the distance rank correlation improves. We can also color the points according to their stability across all the embeddings. Points that are less stable are likely to change their local or global position between two representations. For instance, we can spot that the ends of this cluster move a lot. Selecting them in the UMap shows that the points move to 5 different locations in the t-SNE. We can find out why by highlighting the 10 nearest neighbors in the original data on this embedding. We learn that the points moved towards their nearest neighbors, which are spread over different clusters. If we visualize the high-dimensional distances again for this point, we understand that the two ends of the cluster are closer to each other than we would have expected based on the embedding. Finally, we can visualize the neighbor preservation scores, which tell us what fraction of the high-dimensional neighbors are among the nearest neighbors in the embedding. We can immediately notice that the local structure is difficult to preserve in this large cluster, but that the points in the smaller clusters have better neighbor preservation. Let's take a closer look at this part here. We can assume that the linear structure and the circular shape represent the original structure quite well. We can also check the location in different embeddings and conclude that this subset of cells might be interesting to explore further, as it seems to stand out from the rest. In summary, we have shown you how to use Trace to gain insights into the embedding quality from a global, local, and point-wise perspective. The pipeline and interface are designed to be extensible and scalable. The tool is open source and available on GitHub. We encourage you to try it out on your own data.